Hello and welcome to In Control, the first podcast on control theory. Here we discuss the science of feedback, decision-making, artificial intelligence, and much more. I'm your host, Alberto Padoan, live from a rather unusual traveling recording studio here in Verona, Italy. Quick thanks to our sponsors, the National Centre of Competence in Research on Dependable Ubiquitous Automation. And today with me is our guest, Markos Papageorgiou, Professor Emeritus at Technical University of Crete and Ningbo University. Welcome to the show, Markos.
Thank you very much for the invitation, Alberto.
So, Markos, it's a huge honor to have you on the show. You're widely regarded as one of the pioneers in intelligent transportation systems. You've shaped how stakeholders manage traffic around the world by applying concepts from automatic control theory to traffic systems. I'm quite excited to dive into the body of literature that you've generated as well as the resulting technology. Typically, the way we start the episode, or at least I'm generally curious about, is how growing up in the environment where you grew up affected who you became. So maybe can you give us a brief overview about that?
How early should I start?
As early as you think is relevant.
Well, what I usually say is that our life is like a chaotic system. So some very tiny changes or decisions at some point, lead us to completely different areas. And I have identified in my life a few such points. And one was when we decided with my parents at that time to which high school to go. And I should say I was born and grew up in Thessaloniki, which is the second biggest city in Greece. And then at that time, high school was 6 years. So at the age of 12, I had to decide which high school to go. And without any really pressing reason, we decided that I should go to the German high school of Thessaloniki. This is a private school that is run by the German government. There are such schools in many countries, and there are two in Greece, one in Thessaloniki, one in Athens. And when you visit that school, you get the graduation certificates, both the German and the Greek one, which means that you can study in Germany or in Greece. And then they also gave me, for being between the first three in the graduation, they gave me a scholarship by DAAD, German Academic Exchange Office. And that scholarship would allow me to study whatever I wanted in any German university. So I selected electrical engineering and then control engineering. And second, such tiny decision with chaotic consequences, when I finished my studies, my supervisor, Professor Gunther Schmidt, he had funding in 3 different areas. He asked me to choose among them. And one of them was about freeway traffic modeling and control, and another one was about gas pipeline network modeling and control. And the third one was more theoretical about discrete mathematics in control. So without much knowledge or insights, I just chose the freeway traffic subject. That decision, of course, shaped then my professional future. That all was at the Technical University of Munich. So that's roughly how I, entered the field of electrical engineering, and more specifically control engineering, and eventually I continued with applying methodologies and tools from control engineering into the traffic domain.
I have a few questions actually in that respect. So I'm curious about why choosing a German school, and then why the Technical University of Munich. And I'm also curious why control theory.
Well, some of these decisions, as said, were without much insight or much knowledge, were not completely random, of course, but not really no necessity for that. Well, the German high school, there was a choice between the German, the American high school, or a Greek public school. And without much pressure or wish or whatever endeavor, with my parents, we said, okay, let's go to the German high school. So there was no specific reason. Then once this decision was made, 6 years later, when I finished that school, I got the scholarship. So it was more or less, the way was even more open, even financially, to go to Germany. And of course, the next decision would be which university and what to study. And there, I should say, I was with another colleague at the time who graduated. We graduated together. And we decided to do the same. And we decided, without, again, much very strong reasons, to go to the Technical University of Munich, which was, of course, a very good school. By now, it is even better. It is number one in Germany. But at that time also, it was a very good school. And as a matter of fact, we did not choose electrical engineering. First, we had chosen financial mathematics.
Okay.
Because we liked mathematics, but then we said, pure mathematics might be too theoretical for later professional, activities. And so we chose financial mathematics. But after 2 weeks of classes, we realized it's not what we wanted. So we went to the administration of the university and said we would like to change to electrical engineering. And since we had this TAAD scholarship, we were sort of elite. So they immediately said, okay, you can do that. And then we had chosen electrical engineering, but as a matter of fact, we were not really very keen with practical things, machines, radios and stuff like that. So we thought maybe it's better to take something that is more theoretical, more mathematical, whatever. And that was the reason for going to control engineering. At that time, there was a diploma study of 5 years. After 2 years, you got the first unofficial degree, the 4 diploma, pre-diploma. And then you had to decide among 4 main or 12 finer directions in electrical engineering. And so we went for control engineering for the reason I mentioned.
And I'm curious, so of course, going to German high school, you were probably proficient in German, but I'm curious about the environment over there, like in Munich. Was it very international? The essence of the question is, were you the only ones who actually studied there as international students, or was it a vibrant community at the time? How was it?
No, it was quite international. Of course, the majority or the big majority was German students, but there were a lot of students from other countries. As far as I remember, people from Iran, from Africa, from Turkey, from quite different places. So it was quite international. For us, it was very easy because in the German high school, we had a lot of subjects in German for 6 years since we were 12. We had mathematics, physics, chemistry, biology, all of this in German with German teachers. So for us, the environment in terms of language and even in terms of mentality was not so different than what we were used in the German high school. And as a matter of fact, at that time, maybe even now, but at that time for sure, theoretical, methodological education in Greece was, I dare to say, more advanced than in Germany. So for the first 2 years, whatever we did in mathematics, in physics, chemistry, most of it was already known to us. So it was an easy game, so to say. Of course, later on, we also learned a lot of new things.
Yeah, of course, the tradition continues to date. Some of the best applied mathematicians I know are from Greece or from a Greek background. I'm curious now, so you said that you do your studies at the Technical University of Munich, and then probably you want to continue your path, your academic journey through a PhD, and I guess you choose to continue with control theory, and you're given a range of subjects, and the subject of interest becomes traffic control. So I'm curious if you can give us a snapshot of what was the landscape in research on traffic control at the time?
There was quite some works, going on in traffic modeling and control in various areas. There were, if I can make a brief historical overview.
Let's go. I found the history of traffic modeling fantastic, actually, in preparing this episode. So I definitely want the audience to experience this.
Probably the very first outcome in terms of modeling was in the 30s, 1933, I think, where Bruce Greenshields, who was a sort of traffic engineer, used a camera to try to measure at the same time speed and density. So on a speed density diagram, he had some dots corresponding to his measurements, and he tried to fit a curve. That curve was at that time a line, which is good enough, but there are other possibilities. So a line of decreasing speed for increasing traffic density. So traffic density is number of vehicles per kilometer. Speed is the mean speed of vehicles. So that was probably the very first, or is celebrated as the very first step in modeling. Not much happened in the next 20 years, at least nothing that would be very well known. Then in the 50s again, mostly people from the UK, but also some in the United States, they produced some fundaments of traffic engineering. One of them was John Glenn Wardrop, who I think was an economist. He formulated the famous two principles of how traffic flow distributes in a network. So if you have a network, you have many origins, many destinations, and many different paths connecting every origin and every destination. So the question is, how do human drivers, or how can, in principle, the traffic flow be distributed in this environment, in this network? And the first principle is the user optimum. These two principles are known in game theory. I'm not sure whether they were known at the time, but meanwhile, they are quite known in game theory and other disciplines. So one of them is the user optimum, where everybody decides by himself, and eventually you come up with an equilibrium where nobody can gain in travel cost, which is usually the travel time. So nobody can reuse his travel time by changing the path he's using. So under these conditions, user optimum conditions, every utilized route between any 2 points, any origin and destination in the network, have equal cost. Any utilized route, because there may be other routes that are too costly, too long, too time-consuming, which are not utilized by anybody, but all those utilized, they have the same cost. So this is the user optimum. And then the system optimum is an optimization problem. How could we distribute all this traffic flow in the network such that the average travel time, the average cost, or the total cost, the same thing, is minimized? And the two principles lead to different solutions, because if you minimize the total time spent by everybody, then you get something, of course, lower than in the first principle, but at the price that some people having the same origin and same destination take routes of different cost. So me and you may have the same origin and have the same destination, same home, same job place, but then I am sent via a path that takes less time than you. So, of course, you would be satisfied. And that's the reason why many times systems go for the user optimum, so that nobody feels like disadvantaged compared to other people. Although if you take, of course, the average over different days, you end up gaining on the average. But anyhow, this is another question. So Wardrop formulated those two principles essentially verbally. Then he also formalized them. And that gave rise to, I would say, hundreds of PhD and master theses, maybe even thousands. I don't think thousands, but master, and certainly 10,000s of articles about what is called traffic assignment. So traffic assignment is about how to assign traffic in a network in different paths such that you get either user optimum or system optimum results. So Wardrop was an Englishman, and those principles were formulated in 1952. But there are other names. There is also a gentleman called Webster, who also in the 50s published his rules about how to fix traffic lights. So you have an intersection, you have some demand appearing on the branches of the intersection. How long should be the green phase that every direction receives? How long should be the cycle of repetition of those green phases? And that work by Webster is still in use in many areas whenever you have a signal that does not change in real time based on measurements, that is fixed in that sense. Mm-hmm. And another Englishman, Richard Alsop, who passed away last year from UCL, University College London, also extended or let's say fine-tuned these rules by Webster. And then there was a transport or traffic, TRL, Transport or Traffic, I don't remember, Research Laboratory, TRL, that was a public institute of research on traffic, and David Robertson was for decades the director. And they produced a lot of tools that some of which are still in use, which is not necessarily good, but they are, like Scoot, which was a real-time traffic control system for traffic signals in urban areas. Transit, which was a tool to develop fixed-time signals for a whole network, and other tools. So all these people were from the UK, and so in that period, 50s, 60s, 70s, a lot of results and tools were coming out from the UK. By the way, TRL was privatized at the time of Thatcher. And I'm not sure it exists still now. It existed for a period, but the best scientists, because it had gathered the best scientists in traffic engineering, they just left when it was privatized. So it was the decline of that institute, the way we knew it. And I'm not sure even that it exists today, whether it exists today as a private company or not. It was eventually, active on a private basis for a period of time. Mm-hmm. But of course, the best scientists had already left. Mm-hmm. On the other side, all this was about urban traffic and urban traffic control, essentially traffic signals at intersections. At the same time, in the 50s and 60s, there was some important activity by groups in the United States, which, however, was focusing more on highways, traffic flow highways. So we have the famous papers by Lighthill and Whitham on one hand, and Richards on the other hand, which were published quasi-simultaneously but independently and produced the same result, which was the first dynamic traffic flow model that they produced. Whitham was a very famous, if you Google him, he is extremely famous and has a strong legacy in fluid mechanics generally. And, traffic flow was just probably a nice area to apply some of his methods. And this led to the famous LWR, Lighthill-Whitham-Richards model that is still being used in various forms. At the same time, there was quite some activity on microscopic modeling, car following, essentially. How do people behave as drivers or how does the entity driver plus vehicle behave while following another vehicle in front? And there were some very active people. A lot of them were working on a tunnel, the Holland Tunnel that connects New Jersey to New York. And there they had a quasi-laboratory financed by the Port Authority of New York. They had quasi-laboratory with a lot of sensors that they developed themselves. And, when the first general purpose computers appeared for practical use, that was in 1960-61, they immediately jumped on them to try to make also real-time, control for that tunnel. Some names there are Denos Gazis, who is also Greek origin. He was actually a control engineer, but eventually he worked a lot on traffic. And Robert Herman, very significant physicist who did a lot of other works as well, but he also worked on traffic flow. Well, I mean, there was, in these tools, there was a lot of optimization in signal control algorithms. Optimization was used quite strongly. And also, in traffic modeling, Lighthill and Whitham, partial differential equations for the traffic flow. But there was very little control. And if I remember back to what I was reading when I was a PhD student, in terms of control, there was Harold Payne. Harold Payne was a professor at USC, University of Southern California, produced some very nice works on freeway traffic modeling and control. Eventually, he went to the industry to work there. At MIT, there was a control group. They probably had some funding for some years on freeway traffic control, so they did some work, several people, including Mike Athens, a control professor, Alan Wilsky, also a professor in control. They produced some papers on freeway traffic control. Then there was another control guy, George Saridis. Don't remember which university he was. John Barras, who is still active in cyber physical systems, also produced at that time, in the 70s, some first works on traffic. As said, Denos Gazis was also a control guy. Nathan Gartner at the University of Massachusetts in Lowell. He was working in the civil engineering department, but his background was control. And it's interesting to say that, for example, MPC, model predictive control, the first MPC paper, I think it was the late 70s, it was published.
Yep.
But in traffic control, there were signal control methods by Nathan Gartner, for example, which applied the tool using dynamic programming, but that doesn't change the essence. Talking about rolling horizon, that was the word they were using, rolling horizon. I rarely see, when I read papers, overview papers about model predictive control, I rarely see this prehistory, which is prehistory not only of traffic control, but also of model predictive control. Actually, the oldest paper that I know about is by the same Mike Laffens, that MIT professor, who worked on economics, trying to create a model for macroeconomics. And he talked about not model predictive control, but OLOF, which is open loop optimal feedback. That's how he was characterizing what we know today as model predictive control. And of course, open loop and feedback, they seem contradictory, but this is what it is, because you solve an open loop problem in a feedback way.
Yeah.
So it was quite a good characterization, OLOF, open loop optimal feedback.
Very interesting.
And again, within traffic, with the work of Nathan Gartner and others, also some French people in Toulouse, they were talking about rolling horizon. Mm-hmm. And that was exactly the same as MPC.
Okay, you opened a million directions that I could take lots of assists, let's say. We did have an episode actually with Manfred Morari about model predictive control, and I at some point dug in the literature as well to try and track down what was the earliest ancestor, if you like, of model predictive control. And it seems like the idea, in fact, originates in many areas at different times, and not necessarily these areas where we're talking to each other. My conclusion was that, well, the ancestor of model predictive control was dynamic matrix control 2, used mostly in industry, in the chemical control industry. But this is something that I didn't know about. So
which year was that?
Tracks.
The dynamic.
Exactly. So it was that would have been my question for you. So about this paper by Mike Athens, but the years we're talking about in process control were the late 60s, if I remember correctly.
So it should be, I cannot tell you the exact name, I have to look up for it, but I think it was in the 60s, probably second half of the 60s.
This is then homework that I'll do after this episode, just out of sheer curiosity. First of all, I would like to say, well, basically that I really enjoyed this overview of brief history, if you like, of traffic control. But in listening to this overview, I realized that we actually didn't define what is traffic. And since we are also somewhat mathematically oriented in this podcast, maybe we can give an idea about what is traffic, why should we care about minimizing congestion in our infrastructure, let's say, and also from the perspective of a control theorist, I guess to some it's obvious, but to some it may be less obvious. What are the ways that we can influence and sense these type of systems? And when we talk about, again, mobility systems.
Yes, I think we can characterize these things, but we have to distinguish between three subjects, which is motorways or highways, freeways, same thing, versus urban, versus the notion of network. So start with motorways or freeways. There, or let's step back one thing. If you have one vehicle driving, okay, you have one vehicle driving. If you have more than one vehicle driving, then you have traffic. They have to take care of each other. They have to somehow react facing each other. And also you can look at it macroscopically as something that, as a fluid that is flowing. And if we look at motorways or freeways, then this flow is, as we call it, uninterrupted. There is no traffic light, there are no crossings, you are just let that fluid evolve according to some specific own characteristics, like water, like gas, but they have different characteristics. They have some commonalities, but also some differences. And then the idea is to characterize via modeling this behavior, dynamic behavior, evolution of the fluid. And this, of course, like in other fluids, happens by use of partial differential equations, PDEs, right? So in terms of modeling, if we are talking about motorways, we want to characterize the flowing medium, which is traffic, and we do that with partial differential equations. If we are looking at urban networks, then things are different because you have all the time these nasty traffic signals, traffic lights. Mm-hmm. So vehicles have to stop in front of the traffic lights, and things in terms of modeling become more like queuing systems. If you are looking at one intersection, one junction, then you have, the branches, the approaching branches, they are like queuing locations. Or if you look at the network level, like small reservoirs. And then for the modeling, you look at interconnected reservoirs. Now, you talked about congestion. In the first case, congestion is something intrinsic, is a characteristic of the process itself. Of course, congestion usually appears because there may be an on-ramp that feeds a lot of cars onto the highway, which is already quite loaded, or you have a lane drop, or you have a tunnel, or you have a bridge with lower capacity. But congestion is something that is an intrinsic characteristic of the flow. While congestion in urban areas, you see the traffic lights, and eventually you see if there is a lot of demand, you see the queues growing and then possibly even spilling back at upstream intersections and so on, but it looks more like, a reservoir system. In terms of sensors, the sensors are the same. There is no difference between urban or highway, and there are many different technologies. In Western countries, the most widespread used to be the electromagnetic loops. These are big loops covering the whole lane that are placed below the pavement, and then when a vehicle drives, it gives a signal and you can detect it and process it in an appropriate way. But there are also machine vision, cameras, digital cameras. There are magnetometers exploiting the magnetic field of the Earth. There are light beams, there are many radar, many different technologies, but they are similar or same between urban and motorway. The actuators, if you want to influence what is going on, are different depending on motorway or urban. Urban, of course, is the main one is the traffic lights that we all know. While on motorways, you may have RAM metering, which is controlling the flow entering the highway from the ramps in an appropriate way. Or you may have variable speed limits, where you have speed limits that are not fixed, but may vary over time. And you have gantries that indicate these varying speed limits, and these can influence the behavior of the drivers towards obeying to the changing speed limits, and thereby you influence the behavior of the fluid. You can control also the fluid. Regarding the control strategies, of course they are different because we are talking essentially about different kinds of processes. Difference between motorways and urban networks. But as I said, we have motorways, urban networks, and then there are some aspects at network level which essentially refer to how people choose their routes in a two-dimensional network. How do they choose which way to go if at bifurcations both ways or multiple ways eventually lead to the destination? Well, as we said with Webster, that is the problem of assignment if we want to model how do people behave if they don't have any information or guidance. But of course, you can look at it as a control problem, which is the route guidance problem. How should we guide drivers in a network context, whether urban or motorway or even mixed? What paths should they take? And these started to become an important subject in traffic control in the 1990s. At the time, there were no apps on your mobile phone. There were no mobile phones.
It's hard to imagine. It's hard to imagine for us,
but there were variable message signs. Some of them are still there from that time. For example, in many locations, but for example, because I was active there in the highway area around Paris, which is a very complex network of highways and expressways, you had many different possibilities to choose a different route or a different direction, and then you had a system that would give you either information or explicitly guidance. Of course, today it's done with the phone apps. You have Google, you have InRix, you have TomTom, and many other different systems that guide you. It's interesting to note that when you read, of course, it's not very often because these companies do not necessarily publish, but the question is, what kind of algorithms are they using? And some very rare papers that I happen to see in some conferences, they seem to ignore a bunch of work that was done in this area from many different groups in the 90s, at a time where those apps were not yet existing, but the methodologies are the same, because the problem is the same, of course, with more possibilities.
So actually, maybe this is actually a good point to make a couple of comments and possibly clarifications. So first of all, we started these conversations in a chronological way, and we gave an impression of how the status quo was in traffic control, in particular road traffic control at the time. So I just want to do justice to some of the publications that we're basing our conversation on, or at least that my notes are made of. First of all, for the visually oriented learners, I would highly encourage everyone to look at the CSS Day presentation that you gave in 2024, if I remember correctly. It's called Road Traffic Control, Past, Present, and Future. There will be a link in the description. It gives a very nice overview of all of the aspects that we just mentioned. So how do we model a road traffic network as a dynamic system? What are the typical sensors? What are the typical actuators? And also a bit of the history, but also, of course, a monograph that you wrote in 1983 that is, to this date, still an incredibly valuable reference for the application of automatic traffic control concepts to traffic modeling and control. That's actually the title of the monograph. There will be a link in the description. And also a review of road traffic control strategies. That I find all of them being true gems for those who are curious about traffic. And from my perspective, people should be excited about this particular application because it somehow embodies basically all of the challenges that control is facing even today. So these systems being very large scale, being very complex, giving rise to, if we want to call them emergent phenomena like shock waves, for example. And also the fact that we should model these systems, well, we could model these systems, as you said, both microscopically and macroscopically. So there is also this question of scale and multi-scale modeling, if you like. Plus the socio-technical aspect that actually this is not really a physical system, but it's a cyber-physical system with humans in the loop. So where humans are actually also making decisions that may or may not choose to comply. We talked about some of these aspects in podcast before with Bassam Bami and Miroslav Krstic, but I guess here we're going deep into the application. And one clarification that I wanted to make is what are actually the control variables and how do we decide what is optimal in a certain sense? And I'm pointing towards the notion of fundamental diagrams. I think this is potentially useful also for the audience who is not familiar necessarily with the subject.
Let me step back a little bit and talk about traffic as compared to other fluids from two different points of view. So, for example, water systems, right? Water supply. What is the problem? The problem is that you need to offer to the user water at a given or within a range of pressure, however, minimizing the cost for doing that. But you don't care which particle, which molecule of water goes to which household, right? Mm-hmm. So water is water. Any molecule or any that reaches my home or my industry, it's okay. If we are talking about another kind of system, communication systems, so the particles, for example, the emails, the messages, they have an addressee. So when you send an email, it goes into a path together with many other emails and has to be transferred, but eventually my email has to reach its own addresses, not like water. Not any water molecule is okay.
It's only one email that we care about.
Exactly. And in traffic, of course, you have particles that have specific destinations. So it is similar to communications, but there is one additional thing. This particle has also the power of making decisions regarding how fast, how slow, or which route to take in a network. Mm-hmm. So the routing, actually, if you Google traffic control, just traffic control, you may get more than half answers about communication systems. They are also called traffic control programs, right? And only a minority of what you get is road traffic control. But the additional difficulty is that these particles also have the power of making, to some extent, decisions. So this is one aspect of similarities and differences. A second aspect is what you mentioned, congestion. If you look at a water system, then if you have congestion, if you have higher, or let's start with a simple queuing system. You have a simple queuing system. You go to the airport to check in. You have to queue because the number of counters is less than the number of customers. So you have to queue. So you have some delay, but this queuing or the extent, the length of the queue does not affect the servicing capacity. Counters work at the same pace. But if you go to a water system, then higher queues, higher levels of water in open channels, they lead to higher pressure and higher capacity. While in a traffic system, also in communication networks, by the way, for different reasons, any increased congestion degrades the capacity of the system. So it's like a vicious circle. If you exceed some limits of density, if you push more vehicles into the network than a critical value, then you have lower throughput. And this is like a vicious, like a positive feedback. You can go very fast to gridlock and very strong congestion increase. So road traffic systems are very critical also because of this. If we wouldn't have this degradation due to congestion, then it wouldn't be so pressing to do something in terms of control. But the reason we want to control is because we want to avoid this degradation while keeping the throughput at a maximum level. Mm-hmm. And how can we do it? Well, or what do we want to do? Well, usually what we say, there are many different aspects, but usually what we want to achieve is minimize the total time spent by everybody in the system. So the system optimum solution is what we want to achieve. And in order to achieve it, we need in different ways to improve, for example, the speeds or the throughputs when things are under critical, but when they threaten to become overcritical, when they threaten to exceed that critical value of density, then we need somehow to reorganize traffic or hold back traffic so that this degradation doesn't occur. Mm-hmm. And the reasons for this degradation are different in urban networks than on motorways. Mm-hmm. So this is what we are trying to do then, trying to protect the network from degrading, because this is what we witness essentially every day during the rush period.
Yeah, and one aspect that we didn't mention is, of course, there's a lot to say, and that's why I guess we're going in many different directions, but one aspect that we didn't mention is the detrimental effects of traffic on a number of things. First of all, of course, travel time for the individual users, but obviously if we're talking about, the vehicles that we're talking about are cars, for example, that directly translates into more emissions as well as degradation of the infrastructure. So there is obviously an incentive in trying to minimize that. I was reading some data last year about the percentage of CO2 emissions worldwide globally, and if I remember correctly, we're navigating around 12% or 13% in terms of CO2 emissions emitted by road traffic. Maybe the data are different today, I don't know, given that we also have electric cars, but that's a different subject.
I should say, if I may, I talked about minimizing the total travel time of everybody. Essentially, this corresponds obviously to minimizing congestion. And we know, as you very rightly said, that congestion creates more emissions, more fuel consumption. So if you minimize congestion, you minimize those two as well, because stop-and-go traffic acceleration calls for more fuel consumption, and more fuel consumption, of course, leads to higher emissions. And very important, because we have humans in the loop, is, of course, safety. Actually, safety is number one. You cannot in any way do something that jeopardizes safety, but we know also that in presence of congestion, whether in urban areas or on highways even more, we have more accidents than with free-flowing traffic. So if you reduce congestion, you serve a number of objectives, including travel time, which is decreased, fuel consumption, which is decreased, emissions, which is decreased, and safety accident rates, which is decreased as well.
Indeed, and I'm glad we had this digression, because I really wanted to make sure that the audience has the means, if you like, to also appreciate all the contributions that you've made to road traffic control. I have to say, as many times it happens to me, and I'm completely blown away by the career of people that end up being on the other side of the microphone. The applications of controlled concepts to road traffic, I guess, seem obvious in retrospect, but maybe they were not at the time. And I was blown away, as I said, by a number of the contributions that you did. And at some point, I would like to do justice to the body of work that you produced. Originally, we started this episode by saying that you started your PhD at the Technical University of Munich. I went through a number of publications in between the beginning of the 80s all the way to the 90s, where you delivered to the, let's say, a much broader audience than just traffic or control theory, but actually the intersection of both. And I don't know whether we want to dig into the interplay of academia and research, because this is also an area of control theory that is very much at the boundary, if you like, of application. So the concepts that we're going to talk about now have been applied actually in the world and actually shaped the way we drive around. The first ones that I have noted in my notes, if you want, are MetaNet and Alinea. I would like to talk about both, but I'd like to take your perspective, if you like, on these subjects. So the interplay between academia and industry in this particular sector, as well as the first actual field studies, if we can call them so, I guess so, of some of the concepts that you put forward on the road.
Yes, let's start with Alinea, which is also chronologically earlier. In the 1980s, I was in Paris as a visiting professor to teach a course at the École Nationale des Ponts et Chaussées, which is a Grande École. Now it has a different name, was merged with another Grande École. But anyhow, and then I had a contact with researchers from the French Research Center on Traffic that has also changed names a lot of times. Now it is part of Université Gustave Eiffel, like the Eiffel Tower. Anyhow.
Okay.
And we agreed that I will go to them for a couple of years and do some research and practical application regarding traffic flow modeling, validation with data from the ring road of Paris, Boulevard Périphérique, and RAM metering. Mm-hmm. And they had already an installation for RAM metering at one single ramp, isolated RAM metering. So you just control one single ramp given local measurements. But my task was to go for multivariable control, so multiple ramps. So when I was there, they had already installed 5 or 6 different existing local RAM meters. And I was not very keen to work on that because it appeared to me that's very simple, just one ramp, just one control variable, single input, single output system. I never looked at it very carefully because I thought this is too simple. But they had already 5 or 6 installed and they, tested each one for a couple of months, real tedious field work to be able to compare with in the field. And then they were asking me sometimes, well, what would you suggest as an isolated RAM metering system? And one day I said, okay, after lunch I will sit down and try to develop something and give it to you. So indeed, one day after lunch, I tried to make a very basic analysis of the process characteristics and what you could. Then I came up with an I-type regulator. I saw that if you are really controlling the ramp and you want to achieve something, and of course, I also considered the problem as a feedback problem. All the strategies that they were using and that were used at that time, many of them, hundreds of them in the United States in the field, they were sort of feed-forward algorithms. They were measuring upstream, the flow upstream, to decide how to control the ramp flow. There was no feedback. And of course, me as a control engineer, I looked at the outflow of the system and I measured the outflow in order to decide about what to do with the ramp flow. I didn't care about the inflow, which was a disturbance. Of course, you can also measure the disturbance and do even better under certain conditions, but you cannot be blind in terms of what is, because your goal is the outflow, is not the inflow. So I just designed in 15 or 20 minutes an I-type regulator. And that was summertime, everybody would go to holidays. So I gave it to one of my colleagues there who was in charge of the real-time implementation and left for holidays. And when I came back after a month or so, he said, I put that in the field and it works like nothing else. I mean, it's perfect. So that was the birth of Alinea. But we had a very difficult time even to publish, because the civil engineers, they all looked at traffic from the planning point of view, from the modeling point of view, not from the control point of view, and even less from the feedback point of view. It was against their thinking. The reviewers explicitly wrote, what is this crazy thing? How can you measure the downstream to control and decide about upstream? It's silly. those were reviewer comments. Yeah.
This is wonderful. First of all, I'll give a pointer to the audience for those who are curious about Alinea, where it came from. There's a paper on transportation research record. There will be a link in the description, of course, called A Local Feedback Control Law for On-Ramp Metering. And indeed, my question would have been, what was the reaction of traffic experts in the field? Was it difficult to convince them of the use of these new tools or this new way of thinking, if you like, in regulating the inflow of traffic through ramp metering?
Absolutely. It was very difficult, particularly in an audience, in a community of traditional traffic engineers who never heard about feedback. And it was said against their usual thinking. Eventually, we even wrote some letters at the time. There was no email yet to the well-known people in RAM metering. And I don't want to mention names, but they did not even bother to answer, telling them the strength was, of course, that we had field results, not just field results of Alinea, of the feedback, but also field results comparing for the same site under the same conditions with a variety of all the new other RAM metering systems. And that was by far, and it was also the simplest, by the way. It was no simpler than that, than the simple feedback.
Indeed, maybe if I can jump in for the audience. So Alinea, as you say, is basically proportional integral controller, if I can summarize it to a control audience.
Actually, it is in I-type, only integral. Later, we increased to PI in cases where the bottleneck we're going to control is farther downstream, which means that there is additional dynamics. And that's why we took the PI version. But if you have really, which is in most of the cases, if it is the ramp that creates the potential bottleneck that you want to control, then an I-type regulator is okay.
Is enough.
So that was an I-type, not even PI. When we developed the PI, when we introduced the PI, we called it PI Alinea. Sorry for interrupting.
No. Thanks for the clarification. But as a matter of fact, the number of parameters are essentially one or two. So with the desired set point and the gain of the proportional part, I guess. And that's it.
Very correct. The gain in Alinea is the I-part gain. And we found in different installations at different sites very early that it was, there was a very big range of values where the performance was essentially the same, so it was not critical. What was critical was the set point. So you had to properly take the set point so that you don't underload don't create lower throughput than you should. You're not too restrictive with the ramp, or of course you don't overload. But okay, that was also something that was not too difficult to fine-tune in practice. So I was saying we had the field results, and then from Boulevard Périphérique, and then within a European research project, we got also a possibility to work on a ramp in the Amsterdam Ring Road in the Netherlands, where again the results were far above, better than what they were using up to that point. And the third installation was in Glasgow in the UK within a different European project. And all of these, gave us very much confidence, particularly also the comparisons to other algorithms, and also the strength to say to the community, look, you have to look at that, even if you don't think it's correct to use feedback, because, it's better than others. So eventually we had a sort of breakthrough, or people really looking at it with a different perspective. And even now, any ramp metering paper, or 90, now it's 35 years later, you will find, of course, a reference to Alinea, and sometimes not just a reference, but they use it for comparison or as an ingredient of other tools.
Yeah, it's, as you say, de facto one of the standards, or something that is still being used around the world to this date. I should also mention that there is a nice account that you wrote about, a summary of these field results, again, with Aj Salem, that I didn't mention, and Middleham, called a linear local ramp metering summary of field results. There will be a link in the description. When I was reading this part of the literature that you produced, I was excited myself because, of course, as a control theorist, I can see this being very effective, but maybe in a different field, this was not seen immediately. And also, one question that spontaneously arose was the fact of how difficult was it to convince people also to run field studies about these new algorithms, and what was, you think, the successful ingredient in convincing stakeholders in actually letting you deploy these type of algorithms on real infrastructure?
I should say usually it's very difficult to find authorities that will test your algorithms unless you know them from previous cooperation or you are geographically close to them. For example, a Swiss authority may not be willing to let a Greek professor work in their network actively, in the fields. They would prefer somebody from ETH or EPFL, which is natural, of course. But so I must say it's not really easy. You have to find the channels. But particularly for Alinea, due to the circumstances, the very first implementation was the one that even made us realize that this is something really of value. I had proposed that I-type regulation, but if Habib Bachalem, that you mentioned, my co-author, if he wouldn't go directly to the field and put it in the field, we wouldn't know that it is so good. And then we had the European research projects in which also the Dutch Ministry of Public Works, the Rijkswaterstaat, that's how it is called in Dutch, they participated because they had also a few installations of RAM metering using a different algorithm. So in principle, they were interested to see whether they can gain something by comparing with other algorithms. And so we had the second installation in Amsterdam, and the third was, again, in a different European research project where the authority in Glasgow was involved, and also they opened their system to apply it. So the first steps were rather easy, and that was fortunate because without them, we would not be able to convince not only the community, but even ourselves that this is something of importance. You have to see that it works really in this way, to be sure.
Fantastic. And so I guess that somehow probably propelled your career forward, but at least it gave you a lot of credibility in terms of the applications of these ideas in the context of traffic. I wonder, the other project that we mentioned was MetaNet, that essentially, if I can summarize it very bluntly, it's a traffic simulator that to this date is also mentioned in the literature. I was curious about, and of course I want to understand how that originated, but I was curious about what was the status also of traffic simulators and traffic simulations at the time. So was it easy or was it difficult, and what was available?
That's also an interesting question. In terms of modeling, there were two parallel paths. Macroscopic, fluid-like simulation based essentially on partial differential equations, of course, discretized in space and time. Mm-hmm. And the other path was microscopic. So you have individual vehicles that move in an urban network or a freeway network, and you try to model every vehicle. Mm-hmm. Probably there are questions like these also in other areas where these micro and macro scales exist. In the microscopic world, you have essentially two questions. First, how do people dynamically follow the vehicle in front of them? Mm-hmm. This is the so-called car following question. And we had models developed already, as I mentioned, in the 60s in the United States, which there was a follow-up by many different researchers later on. So that was the car following component of microscopic models. Then there is a lane changing. When do you change lanes? This is the lateral component. Mm-hmm. So you need to have a model that mimics, that describes the decision essentially of the driver to change lane. So these are the two components of a microscopic traffic flow model. While in the case of macroscopic modeling, you have, of course, the conservation equation, which is a standard component of any fluid model, water, gas, whatever, everything obeys the conservation law. You cannot have vehicles appear out of nothing or disappearing. So conservation equation is one PDE, and then depending on, the LWR model is a first order model. It only has the conservation equation and then an algebraic equation of speed versus density, which is not dynamic equation. But if you want to be a bit more accurate, you have a second partial differential equation, which describes the time, development of speed. Speed is not just a function of the local density, but is a function, is a dynamic equation based, of course, also on density. Okay, these two things, micro versus macro, we can talk for hours. Consider, of course, we are talking about microscopic, but microscopic models, it's one ordinary differential equation, right? Maybe two second order differential equation. For what? If you imagine, is for the driver vehicle entity. Mm-hmm. And it is essentially, of course, car following is a feedback law. Yep. It's not an active feedback. This became the case much later now with the adaptive cruise control systems, ACC. But at that time was a modeling. But the modeling is a modeling. What are you doing when you are driving and following the car in front? You are playing regulator. Yeah. You are trying to regulate the distance to the front car, where the set point depends, of course, on the speed. If you have higher speed, you want a longer distance. If you have a lower speed, you have a lower distance. But essentially what you're doing then is to regulate the distance to the front. And this is a feedback. But in this feedback, you have dynamics that are your perception dynamics, vision, processing in your mind, actuation with your muscles, and then the vehicle dynamics, which, of course, if you want to have a dynamic model for a vehicle, it may have dozens, if not hundreds, of state variables.
Of course.
Right? And all these in a microscopic model is summarized in the ordinary differential equation first or maximum second order. Right? Mm-hmm. So we are not talking about real simulation. We are talking about, something that resembles the movement. And the idea is not really to mimic the full, or a specific vehicle driver entity, but to move something that is more or less represented. Mm-hmm. Anyhow, on the top of that, though, we have the network aspect. Okay, if you have an axis, or if you have an urban network, or if you have prescribed paths, those microscopic or macroscopic models are sufficient. But what if you have a network? And you have either people who decide which paths to take, who decide at bifurcations to go left or right, or at junctions to go straight left or right in order to follow a different path. So how do they behave? So you come back to the traffic assignment, to Webster principles, but in a dynamic way, because Webster formulated everything, and also in planning of transportation, this is all static, right? No dynamics. But if you want to simulate, you need to do that dynamically. And that was something that happened in the 90s. Different groups in different countries developed tools to try to incorporate these route choice or route guidance aspects in the simulators, whether microscopic or macroscopic. And that was not a trivial thing. So, and that is happened also with MetaNet. When I was in Paris, as I mentioned earlier, what I had developed was the case of macroscopic modeling with fixed, let's say, exit rates at the off-ramps. No networks, no routing. And that model was called Meta. Mm-hmm. And Then later in the 90s, when all this research was happening around the globe, we actually extended this model in specific ways. Would go too far here but there are papers that describe it, of course, into networks. So that's how we came to MetaNet. So Meta is an acronym, is a French acronym because it was developed in France. Modèle d'écoulement de trafic autoroutier. A flow model for freeway traffic. And then we just said MetaNet in order to mark the fact that we had a tool that is working also for networks under different assumptions.
Again, was it a challenge to convince the community of the use of these simulation tools now? Maybe we take for granted today, but were they as diffuse as today?
Thanks to our cooperation with the Rijkswaterstaat, the Dutch Ministry of Public Works, they knew about MetaNet and they made it the official tool of the Netherlands for freeway networks. So for about 20 years, MetaNet was everybody who would like to have a contract, companies or universities with the Dutch Ministry of Public Works, they had to use MetaNet as a software tool.
And so that was to simulate algorithms that would then be deployed on the road, let's say.
Either that or in order to simulate cases where you want to expand the roads, add an additional lane or construct an additional highway link or any kind even of infrastructure change, not just control.
Yeah, also from the analysis perspective, let's say, of infrastructural changes.
Yes. So this European project, I should say, I mean, it's not very interesting probably for non-European listeners, but the European projects, at least those that we participated, they were really a very fortunate thing because they brought us in contact, particularly for us being in Greece, where all these things were not really very much developed in terms of infrastructure. They brought us in contact with players, with authorities, and also, of course, with partners, universities around Europe, and they opened doors for real field implementation. We're very grateful for the existence of these funding of these projects, which, of course, also were helping us to hire PhD students and researchers and postdocs and so on. But most importantly, they opened the doors for field installations, which were very fundamental in order to prove and in order to understand also some weaknesses of whatever we were producing. But let me say the following. What about microscopic? I mean, as I said, there were some works on and off by others. I almost never at that time worked on microscopic modeling or simulation. And there was also a tool or two tools from the Federal Highway Administration, United States, that were developed, I think, also with academics, but basically with consultants for freeways and a different one for urban areas, microscopic. And then in the 90s, a professor in Spain, Catalonia, from the Technical University of Catalonia, Jaume Barcelo, which is a very good friend still, he decided to push from some administrative difficulties that would be too far to mention here. He decided to create a startup with his people and develop a microscopic simulator, a commercial microscopic simulator, which is what was called right at the beginning AIMSAM. And I must say, when I heard that, I said, but how in the 1990s, I mean, you want to go to microscopic simulation? We have so nice macroscopic models and so on. And he was very successful because he was able to demonstrate to authorities at an even microscopic level that they could better understand what happens if you do this or you do that, etc. So the microscopic modeling, which at that time I was not very fond of, became mainstream in traffic simulation.
And still is today.
And still is today. So I thought macroscopic modeling is the future because of course, it takes much less computational time. You can go and check big networks. And okay, in urban areas, maybe you could use microscopic, but highways, why should you go? I was wrong. So So the microscopic simulation was so appealing to authorities and even companies and so on that was very successful and still is. I mean, by today, every company that is active in traffic engineering and traffic control, or every authority, they use in one way or the other a microscopic simulator.
Indeed. Now, I guess today they go by the more fashionable name of digital twin, maybe, but they seem to be playing a very important role. I just want to give a pointer to the audience. Maybe it's not the best paper regarding MetaNet, but one that I found interesting in preparing this episode was traffic flow modeling of large-scale motorway networks using the macroscopic modeling tool MetaNet. It's published on the IEEE Transactions on Intelligent Transportation Systems. There will be a link in the description, of course. And so I guess chronologically, now we are, as you say, around between, let's say, the end of the 90s and, well, mid-90s, let's say, and to in the year 2000. And we hinted at this other particular problem of influencing routing, depending on whether you're American or British, through, I guess, suggestions to drivers. We are predating the existence of apps like Google Maps or Waze. We're not paid by them, so we're not doing publicity in any way. But it's a problem that you actually do actively think about yourselves, right? There's a paper in 1990 on Transportation Research Part B called Dynamic Modeling, Assignment and Route Guidance in Traffic Networks that I want to do justice to before we actually move on to the next phase of your career. I wonder whether you can spend some words on how did you think about that problem from a dynamic perspective?
Well, again, in the traffic engineering community at that time, even more than today, was dominated by people educated as civil engineers and having worked in planning, transport planning. Planning is very important. There is no city, there is no country in the world that does not have a master plan, planning how many people want to move, how should they move, how can they move, by what means, metro, buses, roads. If we're talking about road network, how big should be the roads? All of this must be decided about the infrastructure. And this is planning, very important. It has nothing to do with control. So how do you plan? Well, you need some model. And not just you need some model, but model is everything. Rather than saying, I believe this road, if we construct it, it will not be used or the other will be, you can try to model it. It's not very accurate, but it's better than just guessing, So many people in transport from the civil engineering were trained also in their studies that we need models for planning. But when it comes to control, modeling is of course also necessary, but it's not the most important thing. Because in control, you have something more important, which is data. In your control loop, you gather data in real time and you react to this data. So you don't care so much what is the exact behavior of the process. You rely on feedback for any uncertainties that you may have. So when in the 90s, the issue of route guidance or information, real-time information, became relevant because there were a lot of installation, not because of the apps. The apps were not yet there, but there were a lot of variable method signs and, people started working on it. There were big projects also in the United States, big projects about how to address this issue in a dynamic setting. And the main approaches that were proposed were, again, modeling approaches. So people were saying, okay, we have paths from specific origins to specific destinations, and with modeling, we can, in an iterative way, try to reach, for example, user optimum in the dynamic sense, Wardrop's user optimum. And of course, me as a control engineer, I thought that does make sense. If you want to do something really in real time for control, it would be better. Of course, you can always do, as we said, model predictive control, which takes solution of an optimization problem online, although this was not what they were doing, but just saying. But if you can do it with simple feedback, it's even better. So I tried to figure out how this could happen anyhow. And the way it could happen was by introducing so-called splitting rate. How should vehicles split at bifurcations? So you have vehicles going to the same destination, you don't care about the origin, and they are reaching at a bifurcation. How should they split? The best you might listen to at that time was everything or nothing. So you take what is the shortest path or the shortest direction, and then you take all of them in one or the other direction. This is like band control, like you have in a electric iron, right? Electric iron, it has temperature control, but it switches on-off control. But given the very strong dynamics along the route, these would create instabilities. You would go on and off, but then the experienced travel time might be. And we wanted to have an equilibrium. So we tried to develop feedback concepts that would work, that would be very simple because we're simple multivariable feedback regulators. And that was the essence of the route guidance work that we did. And we even had the chance at that time to have some installations. Again, within European projects, we had an installation the city of Aalborg in Denmark, also in Glasgow, again in the city of Glasgow, and also in the bigger expressway network of Scotland, employing as much as possible feedback concepts rather than relying on modeling mainly.
It's fantastic. So one thing that I was actually curious about was this to me sounds like you were creating the basis, the theoretical basis for what later became then, I don't know, to define them, like user apps that were given to the users that would then provide suggestions about route guidance. So seeing the individual user itself as one of the actuators that we were mentioning before. The question I had in reading this part of the literature was, again, I struggled to understand what was the picture then, like in the 90s, and this seems to be fairly visionary for the time, given that we didn't have certain types of technologies. And here, I guess, we have to make a clarification about how vehicular technology somehow influence and is influenced by these algorithms, and it's all a dance, a back and forth somehow.
Well, as said, at that time, the actuators were roadside variable method signs. So you would give the same information to everybody. I mean, you could, and we did that in some installations, you could differentiate by destination. So you could say, if you want to go to that part of the city of Aalborg, or if you want to go to that city in the expressway network, take that direction. But that was visible by all. The same instruction was valid for all.
So the information structure was the same for all, basically.
For all, yes. And you could, of course, as I said, you could differentiate, for example, by destination, but still everybody who was going in that destination would get the same information or the same guidance. Of course, you could switch, do a time modulation to try to split, in different directions. But it was not at all the situation like today, where even if people are going to the same destination and are at the same location, you can give them different guidance, which is not stupid, it's very clever, because you want to split. You don't want to have, if you guide them all in the same direction, you may create a congestion there. Then you will you will guide them all to the other direction, then you create a congestion there possibly. You want to split, you want to equalize, you want to balance the two directions. Or, at a network level, the uncounted links of the network that may get congested.
And then, of course, there is a compliance and prediction aspect.
The interesting thing is that at that time, there were some gallops of drivers and even of authorities. Would you like on the VMS, on the variable method signs, on the roadside variable method sign, would you like to see information or guidance? And the big majority of the drivers, they wanted information. They didn't trust the big brother to give them guidance, to tell them, if you are going there, take this direction. They prefer to have information, but information is, of course, a throwback on a variable method sign, even on an app. Mm-hmm. It's very difficult to say I can give you information about the next 2 hops, But what about farther? Your destination may be 10 hops farther. So you cannot have information about the whole network easily on a variable method sign or even on a map. Well, guidance, I made this calculation and I give you what is good for you. But they didn't trust. And also authorities would prefer information because information means, I tell people what I measure after some processing and I have no responsibility for whatever happens. If I give guidance, then people might say, why did you send me to that direction? And that was, I had an accident there and so on. So they preferred not to give guidance, although some did finally, but...
It's interesting how these things evolve over time.
Yes, how they evolve. And now, even to go from home to work, which you do every day, sometimes I look
You
at
still rely on guidance.
On guidance.
It's amazing.
But again, there is still, as said, the companies don't release their algorithms.
Yeah.
And my feeling is that also based on personal experience or what taxi drivers tell you, because they have even more experience, sometimes there is this bang-bang effect.
Okay.
Probably because they are not using a stable feedback algorithm.
That's the next stage of the chapter. We were just saying off the record that traffic is an incredibly fascinating subject for a control theories because it's complex, it's nonlinear. And one of the things that we didn't mention actually is we touched on while talking was the fact that it's also multi-input, multi-output. So far, I guess we talked about dynamic traffic assignment for the individual cars, or we talked about the linear as a single lever, if you like, way of influencing a single ramp meter. Well, a traffic lane through ramp metering. But I guess moving forward chronologically in time, there's two things that I think are important if we see it also from the chaos perspective. So one is the fact that you moved back to Greece at the Technical University of Chania. I'm very curious about what motivated your move. It must have been also a brave move in many respects. And also what I was trying to hint at now. So moving towards multi-input, multi-output problems whereby you don't have a single lever to adjust, but many in principle.
Well, starting from the geographical move, I moved to Greece. I was a professor eventually at Technical University of Munich. There was a gap between my PhD, which was 1981, when I finished my PhD, and then 7 years later, 1988, I became a professor at the Technical University of Munich. I must say that in Germany, at that time at least, maybe even now, to become a professor in engineering, you should have some experience and, a career also in industry. If you would have just many good publications, but always affiliated to a university, that was not good enough for engineering faculties in Germany. To become a professor, you had to really have also practical experience. And so it was not like in the United States, where usually a good PhD graduate may get immediately an assistant professor position. At that time, anyhow, there were no assistant professors in Germany, so I became a professor in 1988. And then 1994, I felt like moving towards Mediterranean, of course, not for professional reasons, because coming back to Greece was not something that would boost my career, but, I was very optimistic that I may still be able to work with similarly well. Because of the European projects, Europe was offering things independently of where you are. But the motivation was that I wanted to come towards Mediterranean. And of course, being Greek, it was more easy to come to Greece. And it was more or less a coincidence that I ended up in Crete, at the Technical University of Crete. And if you ask me what were those personal reasons, I cannot really tell more details. I don't even know myself. I just felt like coming here. At the time I was single, so I thought if I don't like it, I can go anywhere else. And as a matter of fact, 1997, I went the first time to MIT for a sabbatical as a visiting professor and had a graduate course there. they told me, look, at MIT, we are usually not hiring people above the level of assistant professor, but in your case, if you want, we can open a full professorship with tenure if you would,
Wow.
like to come to MIT. And that was just 3 years after I moved from Germany to Greece. And I thought, well, I mean, it's of course a big honor to have such a suggestion, but 3 years then go again somewhere that is even more remote than Germany. I didn't even think about it. And then they continued, though, for the next even 5-10 years to not really to pressure me, but to offer me the possibility to go there. But I didn't want to go. I don't know why. My kids, they sometimes blame me and my wife. Why did you do it? Anyhow, now coming to the other question of multivariable. Yes, I mean, Alinea was a single input, single output system controller. And it was clear that you could do better if you can apply a multivariable tool method, I mean multi-input method. And my first attempt was to use classic linear theory, like linear quadratic regulators, linearizing the process, but it proved eventually, even in the field, to be, not much better than Alinea because of two things. First, if you linearize traffic flow, then all the information flow goes from upstream to downstream. While during congestion, you have the spillback, you have the shock wave moving upstream. And so in the linearization, you lose this component. That was the first thing. The second thing was constraints, particularly when you have ramp metering, you have a limited storage at every ramp. And the classic LQR, of course, doesn't consider constraints, so that was a second thing that was missing. So although I had developed a multivariable regulator that was also quite successful in research, I mean, other people took it over and tried different things, I realized this is not the way to go. And so the next attempt was to use nonlinear optimal constraint control. For huge systems involving hundreds of state variables, dozens of control inputs, and trying to solve numerically a nonlinear constraint optimal control problem. And I mean, optimal control was something that I was using since even my PhD, also in other areas, because there is also some quite interesting research I did for water systems, but we don't talk about it now. So I did have a quite elaborate solver, numerical solver for control problems. So I managed to solve huge problems of the size I just mentioned within 1 minute or a couple of minutes. And that means we could use them in an MPC sense. And that was the tool AMOC. And that tool was for us very valuable because we learned a lot from this tool. I always say to my students, if you have a control problem and you can formulate it in a reasonable way as an optimal control problem, you solve it, you may see things that you don't believe they are optimal. You may think I have a bug in the code or the solver does something that is not reasonable. But then if you scratch and try to understand why is this optimal, then you realize that this tool gives you solutions that may appear counterintuitive, but they are really optimal. And if you are knowledgeable enough regarding the specific application, you may really understand eventually why they are optimal. And so AMOC was like a teacher for us. We had developed something that was teaching us about the properties of traffic and how to control it.
Fantastic.
Yes. And so I was telling my students even earlier with the water systems, we had similar experiences that a good optimal control problem is like an artificial intelligence tool in the sense that it can surprise you. You are the creator of that tool, but it answers, it gives you solutions to specific scenarios that you don't understand. They surprise you, and then you have to try to understand why this is optimal. So the tool becomes more clever than you and produces solutions that you would not imagine. And actually, even at that time, artificial intelligence was basically rule-based. So rule-based, you are never surprised by what it gives to you because you design the rules, and if you follow the rules, you understand why it says what it says, right? It's different with today's artificial intelligence because in today's artificial intelligence, you do have optimization. You optimize the parameters blindly of the neural network in the tool of artificial intelligence. And this optimization creates situations where you are surprised but by what you get from your creature because you have designed that tool. Anyhow, coming back to traffic, we had this AMOC tool, and we had an agreement with the European authority to apply it to a big network. But we were a bit hesitating, saying, you go to the field with something that is a black box for the operators, and it is smarter than them because they just need to follow what it says, but they don't understand why does it say that. And that might be a disadvantage because if you want to go to installations, at least in traffic, you must have the operators, the guys who are running the system and who will run the system even after you go. You must have them on your side. They must feel comfortable and they must feel enthusiastic about the system. Otherwise, if they don't like the system for any reason, it will not live long. And so we decided, based also on the lessons we learned from AMOC, to design something that is more transparent, partly rule-based, partly feedback-based, but more transparent in its actions. You could easily understand why is it doing what it is doing. And that was Hero. And we decided that if we want to go to a field implementation, it's better to go with Hero rather than with MPC using a huge software tool like AMOC. But our agreements with this traffic authority eventually did not go forward for reasons that are non-technical. So we thought, what are we going to do with Hero? And then an unexpected email arrived from Australia, from an authority of the state of Victoria, which is the state of Melbourne, who were sending people all around the world to find out what are the best sensors, what are the best actuators, what are the best strategies, control strategies for their RAM metering system. And they heard our name at many locations. They didn't visit us, they didn't know about us. But many people indicated, ask Papageorgiou. So we got that email and said, we heard about you and we would like to come and discuss. So they came here to Crete and we presented them Hero and its features, and they were very excited and very enthusiastic because it incorporated many things they already had thought about.
Okay.
And so this opened the way for the first installation in Melbourne, which proved extremely successful. And then essentially Hero, what it does is it employs independent alineas for every metered ramp. And then there is a coordination layer, which is a sort of multivariable regulator that tries to activate or to change the set points for individual alineas so that you get an optimum outcome at network level, considering, of course, always and observing the length of the queues at the ramps. And so we ended up with Hero, which was, as said, a success. It is now operational in several states in Australia. It is trialed in the United States, and there are discussions for application in other areas, which is, as we said, multi-input system. There is a single software tool which reflects our control strategy that decides about what to do, having real-time information about the whole network rather than only around the vicinity of a single RAM. And this improved a lot the outcome.
And lots of comments on these developments. As I was preparing this episode, I felt pretty much as I felt when I was reading about Alineo. Again, it must have felt incredible on your side to see the developments and the success that these algorithms have led to. I should mention that Hero is, in particular, I'll talk about AMOC also in a second, received the Transition to Practice Award by the IEEE Control Systems Society. There will be a link in the description, and it's also mentioned as a success story in a document that was prepared again by the IEEE Control Systems Society, where a number of applications, let's say, of control theory are listed as demonstrations of the impact of control itself. So I guess this is a huge compliment and a testament to what Hero achieved in the field. I also want to mention a couple of related publications, again, for people who may be interested in learning about this later after listening to this episode. So for AMOC, I noted down a paper on transportation research part C, emerging technologies, with Apostolos Kotsialos, efficiency and equity properties of freeway network-wide ramp metering with AMOC, which stands for Advanced Motorway Optimal Control. And then HERO stands for a heuristic coordinated strategy. I particularly found it funny that you called it heuristic, although, of course, there are reasons why you use these heuristics. And as you mentioned, the use of AMOC justifies why these heuristic rule-based approaches blended together with optimal control actually makes sense. And yeah, the field deployment of HERO was deployed in Melbourne, and this is also detailed in another publication. I don't know whether this is the most representative one, that goes by the name of Heuristic Ramp Metering Coordination Strategy implemented at Monash Freeway, Australia. Again, also on Transportation Research Record, Journal of Transportation Research Board. From this moment forward, your interest again shifts towards other aspects, if you want, of urban traffic control. What I noted down in my notes is the concept of a store and forward model of urban traffic that goes by the name of TUC. I wonder whether you want to spend some words on this moving forward.
Sure. That was also something that was, at least in its first version, developed relatively fast, because we were working in the European project I mentioned earlier with RAM metering in the city of Glasgow. And there they said, okay, we will apply Alinea, but since we are going to create a ramp queue, people may divert and take the next on-ramp by driving on an arterial signalized arterial. And they had fixed time control for the signals on that arterial. So they said, well, maybe we would need to apply some kind of feedback control for traffic signal for the arterial to accommodate, the additional traffic that might come due to RAM metering. And I had some preliminary work applying linear quadratic regulators to traffic signals using the store and forward modeling that you mentioned. And then I said, look, let's try and see whether we can go forward with that. And we developed that on that occasion and immediately put it in the field before even publishing anything on the methodology. And it worked. It worked very well compared to the fixed time controls. So we understood we have again found some gold somewhere. So we did some additional developments, and eventually we ended up with TUC, which, by the way, is also the acronym of our university, Technical University of Crete. And so the first application was in Glasgow, but then we had another European project where we had a chance to apply it in our city, in Kania, and also in Southampton, where they were using scoots, and also in Munich, a part of the network of Munich. These are, I remember very well when we used it in Southampton. The whole city center of Southampton, about 55 signalized junctions. And then you have made the installation, you have made some dummy control, to see that the software is okay and that it produces what it should, etc. But you don't have it in closed loop. And then the point in time comes where you have to switch on. Meaning that from that point on, your algorithm is controlling a whole city.
Incredible.
50, 55 intersections. And if something goes wrong, of course, somebody is there to switch off to the previous situation, but it's not necessarily what you would like to see.
Of course.
So I had such experience a few times in my career. The previous one was water systems, where you had some huge basins, and all of a sudden you would switch on to your algorithm, and they would work based on your algorithm. And of course, you had simulated that before, and you are somehow confident that it should work, but not fully confident, because real life is always something different when we are talking about not just a motor or something reasonably small, but huge thing involving humans. It's a strange feeling. Anyhow.
I bet.
So that was the creation of TUC, which was then applied also in different places. In Brazil, it has been applied to different cities, and we are now working on a project to apply it in Athens. So I believe this is also something good, but I should say that the limitations or the range of improvement you can have in an urban network, if the demand is really very high, particularly with very high demands, are limited. So you can have some improvement, but it might be that the improvement in very loaded networks may not be as spectacular as on freeways.
Okay, and I guess at this point, well, a significant word that I noted in my notes is something that relates to estimation rather than control. So we've talked about traffic control so far at length, but we didn't talk about the data aspect. So basically, how to take a snapshot of the current status of traffic and predicting traffic in time, so as that the operators actually make use of that information to make decisions, for example. And so the publication I'm referring to is Renaissance, with Yibing Wang and also Albert Mesmer, that you published at ITSC in 2006. This is essentially a real-time freeway network traffic surveillance tool that leverages the idea of a Kalman filter. I'm wondering, how did that idea originate for you?
I must say there was when I did my PhD, there was a essentially postdoctoral researcher, Michael Kramer, who, by the way, also did some significant work in traffic control, but he passed away rather early, so he could not continue. He was, of course, older than me. And also the Harold Payne that I mentioned earlier, professor at USC, had done some work applying Kalman filtering to traffic flow for estimation purposes. But when we did that many years later with Yibing Wang, we took a more comprehensive and more general approach and demonstrated that with extended Kalman filter, with appropriate choices of inputs and outputs, you can do a very good job in estimating the actual, in real time, the traffic flow based on a limited number of local sensors. Because the problem with traffic sensors is that they always give you only a picture of what happens at the location they are installed, which may not be representative for a whole link, let alone for a whole network. So you need a lot of them. There are networks that are very well equipped, like the Melbourne network. They had sensors every 500 meters, so that's ideal. You don't need an estimator there because this is sufficient information. But in many other networks, you may not have that density of sensors, and then it is a very good thing to have an estimator, like an extended Kalman filter. Obviously, we again hit a need when we did that work with Yibing, because for a long time there was no estimation work worldwide. And then after this paper, all of a sudden you had dozens of papers applying extended Kalman filter, also trying to see what happens with other kinds of filters like particle filter or moving horizon, different kinds of filters. So it's created a wave of works that were triggered after that first publication with Yibing, who did an excellent job, by the way. He's now a professor at Zhejiang University in China, who is number 3, I think, ranks number 3 of the universities in China. And we had also some quite successful field applications at that time. Of course, by now, this importance is still there partly, but potentially for the future is diminishing because vehicles are connected. We talked earlier about the apps of vehicles. The apps, of course, it's not only that you get the guidance, also the company that gives you the guidance, they get your position and your speed. And so you don't have just one sensor fixed somewhere in the network, but you have thousands of sensors, individual vehicles moving and producing data of speed. Speed is, of course, accurate because even if you have 5%, let's say, of the vehicle fleet, if you have the speeds of 5% of the vehicles, then that's quite representative of the real speed. But what is not obvious is density or flow, because you know that 5 of my vehicles are there, but how many others are there? In order to tell what is the density or what is the flow, you need not just information from your vehicles, but also about how many others are there. But still, the fact that there are connected vehicles provides better information, real-time information for estimation, which at that time we didn't consider.
You're offering me actually a fantastic assist to move to the next, what I think is an important step in your career, and that's an advanced ERC grant I think it's an advanced ERC grant called Traman 21. That's essentially what I wrote in my notes, where you start thinking about vehicle automations and connected systems, where I think around the year 2010, 2013, basically, so the early 2010s, where a number of questions, I guess, due to a revolution in vehicular technology, generate a number of questions from a theoretical perspective. So the fact that now, vehicles are connected and can be connected to each other, to the infrastructure, or both, I guess, in principle, and how do mixed traffic flows at this point interact? And these are all questions that from then onwards, if I understand correctly, you start investigating and investigate to this date. I'm actually very curious about this artificial fluid concept or traffic fluid that I've seen also online. I know that I put a lot of meat on the grill, but maybe you can give us an overview of all these concepts.
Yes, absolutely. Let me say first, there are 2 ERC advanced grants. One is the Traman 21 that you mentioned, and the second is the traffic fluid that you mentioned last. And their scope is, of course, always about transport and traffic, but a little different. So let me start with the first one, which was, as you said, between 2013 and 2018. And the idea there was the following. We have, as you said, also vehicles. The vehicles have been evolving, of course, for decades, but there was no evolution that would signify something completely different or new paths or new opportunities for traffic control. They were, bigger, they were faster, they were higher acceleration. Okay, all these are changes, but that didn't necessarily change something in the needs or the requirements or the specifications for traffic control. But in the last 10 years, and increasingly in the future, vehicles really get capabilities, as you mentioned, around 2 things: automation and connectivity. Automation means that they can do a lot of things automatically, like car following. Virtually all new vehicles by now have adaptive cruise control, meaning that they can follow the vehicle in front automatically without you doing anything. And connectivity means that they are connected, for example, as we mentioned earlier, to the company that gives you the instructions, but potentially also to a control center, and potentially, not yet, also to each other. So you have a lot of new communication channels that you can exploit to do different things. Usually the first application is about safety, right? Have a vehicle driving, it encounters a shock wave, then automatically it gives information backward to other vehicles behind. There's a shock wave coming, so that the drivers or the automated systems can react to that timely. That's safety, but you can do also a lot of things to change the behavior of the vehicles, even with ACC, such that you get a better traffic fluid. And so this opens new ways to traffic management. And that was the main idea about Tramon 21. How can we revisit all the previous traffic control tools, and how can we possibly develop new control tools that exploit new opportunities that are already there or will be there soon in the future? How can we exploit these new opportunities? And there was also a practical need, because at that time in the European projects, the European Commission, there was an administration at the time saying all we need to do is automated vehicles. If we have automated vehicles, there will be no congestion, there will be nothing. It will disappear by itself, which was wrong. But we had difficulties to bring along traffic control projects. So I thought, okay, let's try with ERC and let's try something new. Because at the time, there were very few people worldwide who were looking at this issue of how to control with vehicles that have increased capabilities. Because at the end of the story, you may consider this thing like you have computers, right? Because vehicles, automated vehicles, they have computers. It's the most important ingredient. It's not anymore mechanical engineering, but it's computer engineering. So first ERC grant, Tramon 21, we tried to see what are the implications of the evolution in vehicle automation and vehicle connectivity, and also, more importantly, how can we exploit the new capabilities of vehicles for better traffic control. And there is a paper in the annual reviews of control which summarizes not all of our work, but most of our work. Specifically, we looked into modeling, trying to see what are the characteristics of the traffic flow under different percentages of automated vehicles at different automation levels. So that is the essential questioning of modeling. Estimation, as mentioned earlier, how can we exploit the dramatically increased real-time information stemming from connected vehicles to improve the quality, the accuracy of traffic state estimation, both on highways, for which the Renaissance tool was developed, but also at urban networks, which is a different kind of system. Then control in many different ways. We exploited many different possibilities with lower automation, with higher automation, with lower penetration, with higher penetration of situations, and tried also new control measures that are not possible with traditional means. They are only possible if vehicles are connected, for example, and you can give different instructions, different commands to different vehicles at different times. And of course, there's a very high flexibility. For example, one actuator we didn't talk much of traditional traffic flow is variable speed limits. You change the speed limits in real time. And of course, this can be done traditionally with gantries that everybody looks at, but you can do it without gantries. If vehicles are connected, then you can send them the desired speed they should use, either the drivers as a recommendation or the automated vehicle if it is sufficiently automated. So that was the subjects treated in that ERC project. Now, the second ERC project was sort of similar but quite different. We were assuming in the second one that we are in the era of very high penetration of very high automation vehicles. And then we were asking the question, how should traffic be organized? Because the traditional traffic with human drivers is determined by a limitation, a perception limitation of the human driver, which is that we can only look at one direction at a time. You cannot look all around. You have to look at one direction at a time. And of course, since the car is moving with relatively high speed, you should look in that direction, right? And this perception limitation has at least two important consequences. One consequence is that traffic lanes were introduced. Not at the beginning of the automotive invention. They were introduced in the 1950s. Before 1950, even in developed countries, even on highways, even on freeways, there were no lanes. I mean, no parallel lanes, no dust lanes. But then, when the density of cars increased for safety reasons, the authorities introduced lanes. Why? Because if you have a lane, you don't float around. You just play car following regulator. It's very simple. You just look in one direction and this is the car in front and you try to keep a safe distance from the car in front. But this has consequences. The consequence is that, for example, the lane should be as wide as the widest vehicle, so you waste a lot of lateral space. Also, when you change lanes, this is very difficult and very risky maneuver, right? Second implication, even when you drive, you look just ahead. You don't look behind or on the side. And this means that the particle vehicle moves in an anisotropic way. That means it reacts to front stimuli, not to back stimuli or side stimuli. This is called in physics anisotropic, in contrast to water, gas, particles that move, they have the same movement in all directions. And this has also implications. For example, there is no pressure in traffic flow because you don't take into account what happens behind you. So even if you have a lot of vehicles behind you, you don't care about it. And this has implications for stability of traffic flow, for efficiency of traffic flow. So we thought, if we have automated vehicles, this is a very different thing. The particle is a very different thing. It has real-time information all around, all the time, reliably, fast, and it makes algorithmic decisions. So why do we need lanes? Second, why should we look just ahead? We can look also behind and increase traffic flow stability and throughput. So that was the idea of traffic fluid. By the way, the idea came to my mind a few months earlier when I was in India and was teaching a course there. And looking at the traffic there, I got this idea about this new concept for traffic organization. And so we got the second ERC grant to work on this. By the way, both Tramon 21 and Traffic Fluid, they have websites, so if you want to get more information and publications and so on, you can get them there.
Indeed, let me point the audience actually to or at least two relevant publications that I think are representative or in many ways representative. Of course, not the entire scope of the research that you did in these two grants. One, as you mentioned, is Annual Reviews in Control, 2019, Motorway Traffic Flow, Modeling, Estimation and Control with Vehicle Automation and Communication Systems. There will be a link in the description, of course. And a paper that I personally found on Archive, in the extended version of the article called Lane-Free Artificial Fluid Concept for Vehicular Traffic. So I have a couple of comments related to both, actually. I'll start from connected autonomous vehicles, and the research that you have done there essentially shows that cooperation increases efficiency of the system. And at the end of the article, the annual reviews article, you actually say, it is worth mentioning at this point that in the frame of the EU H2020 project Inframix, the presented estimation tools and some of the control methods described are being tested in real traffic conditions. And it looks like, in a sense, now the bottleneck is in some level technological, in some level, actually it's more about us deciding to actually deferring more power to automation. So I'm curious about your perspective on this. And second, concerning the artificial fluid, I found it, in a sense, revolutionary, paradigm shifting for sure, very super interesting concept. And the question is essentially the same. So I can see it being optimal in many ways, so the optimal thing to do. But again, how far are we from implementation? And how do we overcome the obstacles to actual implementation?
Yes, that's a very good question or questions. To start with the first, it's absolutely correct. With extended vehicle capabilities, connectivity, automation, you get cooperation and you can exploit this cooperation in order to get a more efficient traffic flow. And what we did in Traman 21 was to look at different problems at different levels of automation, different levels of penetration of automated vehicles and connected vehicles, and developed different, sometimes more comprehensive, but sometimes very specific tools for estimation or mainly for control, which some of them could even be applied today. Others would need some additional developments in the future. We managed within InfraMix project and other European and also company projects to test some of these ideas. We don't have something operational until now, but in principle, these things could be applied either today or in the near future, and that was indeed the scope of Traman 21, to look at the periods between the traditional traffic on one hand and the fully automated traffic on the other hand. At different problems, some of them require higher penetration rates, some of them less, but in principle they could be applied during this transient period, which, by the way, nobody knows how long it will be until all vehicles are automated. As a matter of fact, if you look back 2015, 2016, there were important people like the CEO of Nissan saying that by 2020 we will have the driverless vehicle, which did not happen. Of course, by now, first of all, we do have driverless vehicles, but only in experimental phase, which, however, have driven millions of kilometers. So there is a lot of experience in that. Every company does this because they are afraid that if they don't do it, if they are not prepared, they may be out of the market. If others are faster and people go for automated vehicles, they will be out of the market. So everybody is doing that. Even some traditional car manufacturers that were not very fond at the beginning to go this path, eventually they did jump on the train of these developments. So we don't know how long will be this transition period. Nobody can really predict, and any predictions proved wrong. But for sure, it's not going to take too long, at least not for highways, for example, where the situation is more clear than in an urban network where you may have pedestrians, you may have other, things. Then traffic fluid looked really at the future situation where most vehicles are automated. And there we got this very interesting idea. We said, what is a fluid? What is a traffic flow? It's the outcome of the movements of individual vehicles. And if they are moving lane-free, like a fluid, there is no lane, and also in an isotropic way, taking into account vehicles all around. And so the question of going from the micro world to the macro world and back is even more, natural to pose. What I mean is you design a control strategy, because you are talking about automated vehicles, a control strategy that is good and efficient and safe at the micro level for those particles. And you make some choices, and those choices can only be guided by what? By safety, you have no crashes, and by convenience for the passengers, meaning you don't, shake them in the car, you don't have too strong accelerations, decelerations, steering, and so on. So these are the two things you can do microscopically, right? But then the efficiency at the level of traffic flow is something macroscopic. To see that, you have to go to the macroscopic world. And of course, there is the possibility to design the strategies in microscopic level and then to simulate to see what are the consequences at macroscopic level, and then go forth and back to see what choices at the microscopic level would not affect safety or convenience of passengers, but would improve the efficiency. And this is what we did, but we also did it more formally, mathematically. So with some collaborators under the lead of Professor Iason Karafillis, who is a control theory professor at University of Athens, Technical University of Athens, we designed controllers for the microscopic level, and then we translated them formally into macroscopic flow models. And this translation is such that, to a large extent, you still have the same parameters of the microscopic level or the same functions used in the microscopic level. You see them appear at the macroscopic level. And so you have a much more direct possibility to create a traffic fluid at the macroscopic level with desired characteristics. And that was the idea, to be able, in all my previous work that we also talked about, we were modeling traffic flow as an external process, right? You get data, you try different assumptions, hypotheses, PDEs, and so on, and calibration to model it as accurately as possible. But now we get the possibility not to model, but to design it actively. And in that sense, we dared to talk about artificial fluid because it's engineered. I mean, you can, to some extent, design it the proper way, and the way of designing it is by appropriately designing the movement strategy at the microscopic level.
Fantastic, fantastic, completely visionary. And when I read this paper in particular, I was completely blown away. Like, I felt that I'm reading something that gives me a glimpse of what is, okay, we'll talk about whether this is necessarily the future, but it looks like it must be the future. In particular, a sentence that struck me was in the abstract, actually, where you say, the proposed concept provides for the first time since the automobile invention the possibility to actively design rather than describe the traffic flow characteristic in an optimal way, i.e. to engineer the future CAV, CAV standing for Connected and Autonomous Vehicle, traffic flow as an efficient artificial fluid.
You're talking about the paper in Proceedings of the IEEE, right?
Yes, yes. Not sure whether I did mention it.
That was, at that time, it was the idea that is expressed the way you did it. But there is a paper in Annual Reviews of Control again, of either last year or this year, with Iason Karafillis as the first author, which describes the way you can do it based on equations and mathematics at the micro and the macro level. Because at that time of the first paper, it was the idea, but no realization yet.
Fantastic. And very much looking forward to seeing this actually in the real world. At this point, actually, I think we're gradually shifting towards the end of the episode. I must ask, what are your speculations or predictions about the future of road traffic control and what we're going to see? Because so many of the ideas that you put forward were ahead of its time, as you've demonstrated also in the field. So you must have an interesting perspective for sure.
Well, I mean, my prediction is, not just mine, of course, many others, is that vehicle automation will continue. Already we see with Tesla, with some other models by other companies, with some Chinese models, we see vehicles that are practically automated, even in urban environments. Of course, legally, the driver must be there and must be ready to take over, though we do have also the automated taxis in the United States. Many different companies run completely driverless taxis, now also in China. So what I'm trying to say, technology essentially is there, 99%. Governance sometimes hesitates, but we are going in that direction. And there will be vehicle automation. Now, regarding the traffic control, despite automation, there will be always the limitation of capacity. So if you have very high demand, you may end up with congestion, exceeding the capacity and having congestion. And in those circumstances, you need traffic control. Some of the traditional traffic control, like RAM metering, may still be valuable. Also variable speed limits, but in a different way of implementation. Traffic lights, I'm not sure. There are a lot of works by many groups, including us, working on intersections that run without traffic signals. It may take some more time, but this may also happen, at least at some locations. So traffic control will still be needed. Part of it using still, traditional algorithms, but some control measures using novel ways. And some of them being completely new.
It's incredible how dynamic is the landscape of traffic, because one always thinks about infrastructure that tends to be legacy infrastructure in a sense. And so the timescales seem to be very long. But in fact, as we've demonstrated in this episode, they're actually quite short, given all the various revolutions that we talked about. There's one question that I would like to ask you that is unrelated to traffic, that is something that I tend to ask to every guest on the show, because we have the opportunity to hear the experience and the opinion of eminent experts in the field. And that's about advice to future students. So something that, if you like, you wish you would have known when you started, or you think made a difference in your career. What would you say to future students approaching the field of control?
Well, the bad news for people who are starting now in any field of research is the plethora of information. So many papers, so much information, so many things to read, which is not always rewarding. I mean, it's not really the information. The time you spend is not necessarily always worth the information you get. So what I always say also to my students is, try to understand, since you chose to work in this environment or you happened to work in this domain, try to understand what is going on, picking the correct, sometimes you may do mistakes, but the correct papers to read, the correct information to get. But anyhow, beyond papers, you need to feel that you have an understanding of what is going on. And then you can start questioning what is missing, or what could make it better, what could improve it, and trying to focus on such questions so that you target things that are worth pursuing. If we are talking about applications, worth pursuing from an application point of view, because they have promise for improving whatever the system is you work on. If it is methodological, of course, a bit different, but still what you could improve potentially to extend applicability and extend efficiency, or extend the range of applications of a specific method.
Generally speaking, I completely agree. In particular about the plethora of information that we keep witnessing. At some point, I think there will be, well, maybe it already is there, a necessity of filtering and curating information, or the massive amounts of information, assuming that's actually possible, because maybe that's actually something that is not possible, but I guess we'll see. Yeah, so this brings us actually to the end of the episode. Just want to thank you for your time with us, Markos. It's been a real pleasure. Thank you so much.
It has been a pleasure for me, Alberto. Thank you very much for inviting me to this. I have listened to other podcasts from this series, so I'm very glad and honored to be in the series of very, very distinguished colleagues, much better than me, who have been in the same series. And thank you very much for the invitation.
Thank you for listening. I hope you liked the show today. If you enjoyed the podcast, please consider giving us 5 stars on Apple Podcasts, follow us on Spotify, support on Patreon or PayPal, and connect with us on social media platforms. See you next time.